So thank you, Joseph, for that very nice introduction. Yes, as Joseph mentioned, I'll be talking about some of the work that I've been working with Joseph and the rest of his group over the past 3 years or so regarding these P-wave interactions between spin polarized fermions and three-dimensional optical lattices. And so for those of that, oh, whoopsies. Am I not changing here? Excuse me. Oh, no. There we go. Okay, I think it was some sort of pop-up on my computer screen. For those of you that recall, I actually gave a talk to the CQIQC about 1.5 years ago, back in December of 2021. And as Joseph mentioned, that was during the height of the COVID pandemic. So this was virtual, and now we get to be in person. And don't worry, you don't need to remember anything about that talk, as I'll go ahead and review all that sort of discussion. But basically, I presented some what I'll call early access data on some of these P-wave measurements. And so since then, we went back to the laboratory and conducted a lot more experiments, took some more data. We found some very nice theory collaborators, all of which culminated in that publication that Joseph mentioned earlier. And so today I'd like to sort of present kind of a holistic perspective on how I think you can perhaps use these kinds of P-wave interactions in these optical lattice systems for the purposes of quantum simulation. So with that, before we get started, I just want to acknowledge the experimental team, both the experiment and on the theory side. And in particular, I'd like to highlight the two graduate students, lead graduate students on this project, Vijan and Pehan, who I'm sure many in the audience know, who graduated recently in the past, earlier this year or so, and have since moved on to greener pastures. And of course, I'd like to acknowledge our very, very wonderful theory collaborators at Gilead at Boulder. Great. I'd also like to point out that we are located in the basement, which probably some of you have been to our labs, but if you want to come see the experimental apparatus or come have a chat with us, you can find us here. I promise we don't fight. Great. So for those of you not familiar with this sort of field of using trapped atoms for quantum simulation, let's just go ahead and review the basic idea. And this is sort of the framework in which I want everyone to think about these P-wave interactions, which is this concept known as quantum simulation of neutral atoms and optical lattices. And the basic idea is that I can say take some laser beams, and this creates sort of a standing wave and intensity pattern. And what I can actually do is trap neutral atoms, say of some spin, inside this light potential. And this creates sort of a synthetic crystal where this crystal is defined by the optical potential that I defined. And it turns out that in these sorts of systems, this allows us to simulate or emulate a wide variety of phenomena in condensed matter experiments in theory. And so this is sort of the framework for the experiments that I want to discuss now, except for the fact that because we're using optical potentials and that we're considering massive particles like atoms, all of the energy and density scales are going to be taken down by many, many orders of magnitude. So your intuition in terms of time scales and energy scales will be something like tunneling times on like hertz to kilohertz time scales, where my lattice spacing is something like 0.5 micron. And you can compare and contrast that to actual solid state materials. So these are the kinds of systems we're going to be thinking about. But I want to kind of step back further and not really think about sort of the physics that you can study in those kinds of things, like say, quantum phase transitions or dynamical processes, but to really think about this from a toolbox perspective, that we are essentially quantum engineers for lack of a better terminology. And we can think that we have some tools available for us for quantum simulation. And without going into too long of a list, here's just a sample of things that you could potentially do with these kinds of systems. You could say, take your laser potential and say, modulate it in time periodically in a technique known as flow K engineering, which allows you to say, control dynamics or engineer some topological hopping terms. We are also able to say, read out the spin and charge degrees of freedom in these optical lattice systems with single site resolution. You can also say, start to realize non-trivial typologies by using unique laser beam configurations, which Professor Brown gave a talk on this a few weeks ago, if you recall, and allows you to realize hexagonal, triangular, or even Kagome style geometries. You can also start to introduce disorder in these kinds of systems, say by adding a speckle pattern to your optical potentials, or say by using some unique geometries, which allows you to say introduce quasi-periodicity. But in particular, the highlight of this particular talk is going to be our ability to tunably control interactions between atoms in these lattice systems across many orders of magnitude, which I'm showing you here. And this is via a mechanism called a Feshbach resonance, which we're going to go into detail about. Of course, there are many, many other sorts of experimental techniques, but this is just sort of give you an idea of the flavor of things that we can do in the lab. Great. So in this talk, I don't know whose mouse this is, but it's kind of annoying. It's not mine. Okay, whatever. Okay, so in this talk, I'll show you how we can begin to generate controllable and elastic P-wave interactions in these lattice systems. And I'll define all these terms for us. So if we're talking about interactions, let's go ahead and go back to basics and just review the simple scattering problem between, say, two atoms, which is going to generate these interactions in these lattice systems. And so under reasonable assumptions about some interaction potential, I can decompose my wave function to, say, my scattering wave function into, say, some relative coordinate, some center of mass component, and some spin component. And in sort of the familiar way, I can expand this the relative portion of this wave function in terms of some partial wave expansion, which has some well-known parity. And in particular, today, I like to focus on two flavors of interactions that we can introduce, which are the lowest order expansions in this partial wave expansion, which in particular, the L equals 0, which is the so-called S wave interaction. And in this talk, I will be focusing on the L equals 1 or P wave interaction. Now, importantly, if I'm considering, say, fermions acting inside my optical lattice, I have to obey exchange statistics. And so I'll pay attention to this parity state, or the parity of these collision wave functions. And in this case, because this is even, I'll need to consider, say, a spin singlet state, where in contrast for these P wave interactions, I'll be considering, say, some spin triplet, which is symmetric. And of course, because it's L equals 1, I can have a variety of collisional channels with different orbital angular momentum. Okay, so just going into a little more detail, of course, you can expand these partial waves, or this partial wave expansion. You can express any sort of collision event in terms of collisional scattering phase shifts, which are these deltas, which in the low energy limit, which is appropriate in these cold atom systems, can be given characteristically by these these effective range expansions, where I expand these scattering phases in terms of the wave vector of my collision, as well as a scattering length A or a scattering volume in the case of P wave. I'll also point out that the next order term is given by these R terms, which is the effective range. And so what we are going to do in the lab is we're going to be able to control these scattering phase shifts by tuning these scattering lengths and scattering volumes respectively. I'd also like to point out a special case, which is you'll notice that these phase shifts sort of go as the inverse of these scattering lengths. And in particular, see that when the interaction strength is very large, which is when these terms diverge, that corresponds to a phase shift of pi/2. And in the case of, say, an S-wave scattering event, this allows you to study interesting physics, such as the BCS-BEC crossover, where when this scattering length diverges, you're at this unitary point, where physics is governed by the product of the Fermi wave vector and the scattering length, and allows you to study some universal scale invariant physics here. So the point of this slide here is that there are some really interesting things that you can study when these interaction strengths become quite large. Yes?
What does it mean to have like even exchange parity and odd exchange parity?
Sure. So if I have indistinguishable particles, if I have fermions or bosons and I exchange them, then Fermi statistics or quantum statistics dictate that that exchange operation has to have a plus or minus sign. So if I have some pair of atoms which are indistinguishable, then I have to obey some particle exchange statistics, which is encapsulated here. If you look at, say, some relative coordinate, so because the center of mass coordinate is going to be symmetric, if I look at, say, this scattering wave function or this YLM, you can see that if I were to exchange the two particles, i.e. switch R for minus R, I get an overall minus sign in the wave function. And that's how I can encapsulate that. Does that answer your question?
So like you have two fermions.
Yeah.
And then I want to have, if they're just both in the ground state, do they have even or do they have odd exchange?
Well, so I mean, there's no, yeah, so this S wave is going to be a lower energy, so I'm going to need to have a spin singlet state. I'm not sure if that answers your question, though.
It's okay.
Okay, maybe your question might be more answered directly when I talk more about what these wave functions actually look like in our lattice system. Okay.
I'm wondering if the point you're missing is that for fermions, the entire wave function will have to be antisymmetric under exchange, but that includes the spin part and the spatial part. So if the spatial part is symmetric, you have to have an antisymmetric spin part, which is what Cora says here, spin singlet state.
Yeah, so if you're working with like a boson sign condensate, of course, you're working with boson. So this exchange symmetry doesn't have a minus sign, it has a plus sign. Okay. So this is kind of where the talk's going to get a little more technical. Yes, question? Sorry, could you repeat your question?
So the first
This is a scattering phase, and this K here is the wave vector of the collision, which is something like you can imagine goes as the energy of the collision. So this is just an expression of a partial wave expansion for a generalized collisional event. Perhaps I'm misunderstanding your question. Great. So now this talk is going to get a little more technical because, we're talking about this tool, and now I'm going to go into details about how we can actually engineer this tool. And this coupling mechanism is known as what a Feshbach resonance is. So the basic idea is if I have two atoms, they're going to be interacting by some Leonard-Jones potential, some 12-6 potential. And so if I have sort of an entrance channel, which is these colliding atoms, they're going to interact with this scattering potential and come back out, and that's the origin of my scattering phase. But of course, because these are atoms, there's actually going to want to form some molecular state, which is represented by this red curve, which we in the field call a closed channel. And the key fact here is that because the scattering states and these bound molecular states can in principle have different magnetic moments, I can change any sort of resonance condition between them through application of a magnetic field. And you can imagine that when this bound molecular state comes close in energy to my entrance scattering channel, that can influence the scattering properties quite widely, and that allows us to tune the interactions between these two atoms. And so schematically, it looks as follows. So here on the x-axis, I am plotting the magnetic field away from one of these resonances. And this blue curve is the energy of this bound molecular state, where here the dashed line at 0 corresponds to the 0 energy limit, which is, say, the limit for, say, two atoms scattering with 0 energy. And what we can see is that as this bound molecular state is brought closer into resonance, it experiences this classic level repulsion with the scattering continuum, and that manifests as this very classic resonance profile in the scattering length. And so this is known as a Feshbach resonance, and this is going to be our ability to tune interactions, say in particular, for this case, the S wave scattering length. But you can imagine a similar story will happen for a P wave collision as well. And so this is the tool that we're going to be using to generate these interactions. And it turns out, yes?
When you say interaction, then like there's a frequency associated with the oscillation between two states, both channel and space, or Like, so what is the interaction?
Sure, of course. So when I'm talking about a scattering length, I'm talking about a scattering problem, right? So there's no bound states in this particular case, right? So we're just thinking about having a free scattering state coming in, and there's going to be some interaction potential, and it scatters back out. So from this perspective, I'm not considering driving, say, oscillations between this scattering state and a bound molecular state. But if you wanted to, there are experiments that you can do where you can actually transfer these two atoms into a bound molecular state. So you can do those things, but that's not the focus of this particular talk.
The larger interaction state, the larger scattering.
Yes, yes. Great. And so the atomic species that we're talking about today is potassium-40, which is a fermionic isotope of potassium, and in fact exhibits two Feshbach resonance, one of these S-wave flavor, which exists between the spin up and spin down, which we call an AB collision, and also a P-wave Feshbach resonance, which exists for, say, two spin up atoms, which we call in the BB state. And so this S-wave Feshbach resonance has been used quite extensively throughout the field, but this P-wave one is a little bit more tricky to work with. And I'm going to talk about why that's the case. So the first reason is that there's a significant three-body loss associated with this P-wave Feshbach resonance, which is basically the precursor to solid formation, which is where all the atoms want to come together and make a solid. And the fundamental problem is that these P-wave collisions are going to be energetically suppressed by a centrifugal barrier. And so naturally speaking, these interactions are quite weak. And so when we try to resonantly enhance them, or this requires the resonant enhancement, but this also will increase any three-body loss. And so here what I'm plotting for you is this seminal work back in 2003, where the x-axis is the magnetic field around this P-wave resonance, and the y-axis here is this three-body loss coefficient, which you can see diverges as we approach the Feshbach resonance. And so that's problem number one. Problem number two, though, with this P-wave interactions, which is in the case of potassium, if we were to say make a molecule from this molecular potential, the lifetime is actually quite short. It's around 1 millisecond or so. And so if you compare that to typical timescales of these quantum simulation experiments, this is a little bit too short to be actually useful. I will point out that though this loss mechanism is specific to this atom, and this comes from spin relaxation, which is a consequence of the fact that the scattering state that I'm considering here with this up actually corresponds to the second excited hyperfine state. And so the atoms can actually energetically relax down to an AB through some higher order collisional event. And so this loss mechanism doesn't exist in other atoms, say, such as lithium-6, for which we can say uses Feshbach resonance in the AA channel. So this is a little bit technical, but the punchline of these two slides is to say that three-body loss is the main problem that exists in trying to use these P-wave interactions. Two-body is also a problem, but is very specific to the kinds of atomic species that you're working with. So it's less of an insurmountable issue. But the main problem is three-body loss. So you might be thinking, okay, so S waves are great, P waves are a little bit more trouble. Why would I want to work with them in the first place? And so without going into detail, there are a couple of broad interests in the applications of P-wave Feshbach resonances in these condensed matter, or these cold atom systems. And broadly speaking, you can begin to say realize some exotic superfluid phases. There are also some interesting Efimov few body states which you can hope to realize. And actually, there's also applications toward quantum information. And for references, I would direct you to these papers over here if you'd like to learn more. So this is sort of our goal, is to be able to realize these P-wave interactions, but we have a couple of problems, which are these three-body and two-body losses. And so the way that in our experiment that we circumnavigate these issues is by working sort of by skipping the bulk step. So we avoid working in a bulk and we go straight to working with these atoms inside an 3D optical lattice potential, which I'm showing you here. So this is a simple 3D cubic lattice where each of these intersecting points are where atoms can live. And you can see that on each of these sites, I can say have one atom, a pair of atoms of different configurations, which will go into more detail. And in particular, I'm going to be working in the so-called deep lattice regime, which is where if I can suppress tunneling by increasing the potential depth of any of these well sites, And so this means that the typical tunneling times are going to be much longer than any relevant experimental timescale. So for the purposes of this measurement, I can consider all these lattice sites to be isolated, and it turns out well approximated by a harmonic approximation, where the trapping frequencies of any one of these lattice sites is the order 100 kilohertz or so, where this energy scale is set by the natural energy scale of these lattice systems, which is defined by the mass of my particle, as well as the color of light that I'm using for my optical lattice. And so, as I mentioned before, this results in a variety of two particle and single particle states. I can say have some empty sites, single sites, or some double sites. So this is the system that we're going to be working with. And now I'm going to go into more detail about sort of what these two particle states are, which are the things that we're going to want to generate and study for these P-wave interactions. So as a reminder, these wave functions can be decomposed into a relative and center of mass and spin coordinate. But for now, we're just going to focus on this relative coordinate. Now, because each of these lattice sites are well isolated and are well approximated by a harmonic potential, I can just think about these pairs of atoms living in different oscillators modes. And so in the case of working with a spin singlet, right, because it's even, it can have, or because it has an odd spin, it can exist in this even parity band. You know, have a relative wave function that looks just like the ground state of a harmonic oscillator. Or in the case of, say, this up spin configuration, it's going to have to live in this first excited relative motion, which has some odd exchange symmetry. And so these are the individual pair states on each of these lattice sites that we're going to make. And in particular, I would like to be able to probe these sorts of states like this and measure, hopefully measure and tune any P-wave interaction between this pair state. And so the way that we can actually do this is sort of a very well-known approximation, which is this concept known as a pseudopotential, which is a way of approximating any interaction on this lattice site in terms of the scattering volume or the scattering length. And although you could treat this perturbatively and just use these wave functions to calculate some interaction strength, it turns out that in this limit, there's actually some analytic forms for these interaction energies at all energy scales. And so it's these sorts of interactions which we would like to probe. So now we'll go ahead and talk about how this experiment is actually conducted, and so how we actually engineer these doubly occupied sites. So I won't go into too much detail unless you're curious, but the basic idea is that we start off with a spin mixture of a degenerate Fermi gas, and we adiabatically turn on the lattice potential. This is a sort of a one-dimensional cartoon, but it extends to 3 dimensions as well. And the basic idea is that as long as our temperature is much, much smaller than the band gap delta, and if we choose an appropriate tunneling and interaction strengths as well as filling fraction, this is preferentially going to create a large number of these spin singlet states in the ground relative motional band. And so once we do that, of course, we want to make a spin triplet in the excited relative motional state. What we do is we apply an optical Raman pi pulse, which excites this the singlet pair state in this ground oscillator mode to a triplet down-down in the first relative excited mode, which doesn't exhibit a P-wave interaction. But then we can probe this P-wave interaction via 2-photon RF spectroscopy, where we flip both spins, so say from spin down-down to spin up-up. And you can imagine that if we have any interaction present in the spin up-up, that's going to modify the spin flip resonance condition here for 2 photons by this interaction energy UP. And what we'll do in post is measure the normalized magnetization M here, which is simply just the spin contrast between the different spin species in the system. So I'd like to go a little more detail about how the measurement is conducted. So because we have, of course.
Sorry, the 2-photon RF spectroscopy is between the down-down and the up state?
Correct.
I'm surprised to do that with only 2 photons because you have to flip both spins.
So it is true that this is RF spectroscopy. Yeah. So the idea is that, yeah, if I'm trying to go from this state, just spin singlet, to this triplet state, there's going to be a spin and motional degree of freedom change. This is sort of technical, but a Raman transition is going to be broadened because of inhomogeneities in the beam. So it's sometimes convenient to separate sort of the spatial and spin degrees of freedom, which is why we do it in this sort of two-step procedure, where we first sort of encode the motional degree of freedom first, and then separately do the spin degree of freedom through this R spin flip. Yes.
What are you using to create this harmonic potential?
The harmonic potential is provided by the lattice. So the optical lattice creates a standing wave in intensity, which is a sinusoidal pattern. And when the lattice depth is very deep, you can imagine just doing harmonic expansion about this lattice potential.
So then the wave function is wave function of relative coordinates, right? So how does that fit into this harmonic potential?
Great. Yeah. So it is true. It's a good question. So it is true that if I look at the total wave function of this pair state, it's going to have multiple components. It's going to have a relative center of mass and spin degree of freedom. But you can imagine that from the perspective of the interaction, the center of mass per part is not going to participate in the interaction under some reasonable assumptions, which we can talk about. But it sort of is just a spectator in these sorts of interactions.
So you said the type of the harmonic potential is created by the dipole type force, which would be which I would imagine is the center of mass motion that is the harmonic potential, not relative or relative motion.
So I'm not sure if I answered your question as though.
If you have a harmonic potential created by the optical lattice, it will be the center of mass motion that's in this harmonic potential, not the relative.
Sure, but if I have two atoms and they're moving with some center of mass motion, you can imagine that, I mean, for a collision to happen, what matters is the relative motion between two events, right? If I were to have two particles and they just move like this, they're not really going to be interacting with each other. The interaction comes from the fact that I can change the relative separation between them. That's what a collision is, right? If I have two scattering wave functions, they need to come together. But if they're infinitely far apart and they just travel together with some center of mass motion, there would be no interaction. So what's important here is the relative coordinate.
But they both see harmonic oscillators, right? Because R1 and R2 are both in the harmonic oscillator, so the potential is R1 squared plus R2 squared. With the change of variables, that's the same as R1 plus R2 squared plus R1 minus R2 squared. So the harmonic.
Yeah, so I guess, yes, you can also imagine that this, so I can just talk about it now because you're curious, is that this separation breaks down when I'm no longer in the harmonic regime. So if you were imagined to include some quartic term in the potentials, then you're going to get coupling between a center of mass and relative degrees of freedom, which is in fact a effect we have to account for in our data.
But I think when you take into account more than one harmonic potentials, you're picking J here. So as soon as J comes in, then there's a center of mass.
Sorry about that.
The pairs are given in the different harmonics figure. So then center of mass will have some interaction because you take the tunneling between them, unless you are taking completely non-interacting pairs. Are you doing that approximation?
Sorry, I'm not sure if I understand what your question is, though.
So can you change the slide? You can move back. So move to the many of the sides potential. Next slide. Next. Move to the probably the last one you had.
Sorry, I'm not exactly sure.
Next one with
The question is basically, how can you ignore tunneling?
yes. Tunneling, you have a more.
Certainly, of course, yes, I 100% agree. Yeah. Sorry. Yes, sir, I 100% agree with you that, yeah, if I have tunneling between these between the sites, then this perspective of these individual harmonic sites completely breaks down. And it's not appropriate to think about these as some sort of isolated states. But the point is that we're working in the very, very deep lattice regime, where I've completely suppressed tunneling with respect to all other energy scales. And so it's appropriate to think about this as a separated array.
For optical, the code that you had, the last slide where you start.
Spectroscopy slide.
Spectroscopy slide.
Sure, of course.
There you go. Yeah,
Mhm.
so are you taking one lattice, the harmonic oscillator and the other completely independent here?
So this is happening on a single lattice site.
So just
Yeah, this perspective is a single lattice site.
so you'd expect to have all of lattice effectively having the same phenomena.
Yes,
which
exactly.
probably requires a little bit of correlation among them. Should be some collective.
Yeah, so I'm not sure if this exactly answers your question, but so first of all, I just sort of put that. So this is happening on a single lattice site. So we're not considering, again, no tunneling suppressed here. So it's appropriate to work in this single site basis here. And you're right, this is going to happen across the entire ensemble. But because of the fact that we've worked in this large lattice depth, and we initially load our sample, we increase the lattice depth, and which decouples all of them. So if there was any coherence between neighboring sites, it's sort of lost by the fact that we turn up this very deep lattice, and there's going to be some decoherence time between each of the lattice sites. So in this regime, if there were, you could imagine that if I were to work in a lower lattice depth, I could have coherence between each of these individual sites. They don't talk to each other.
Preparing them all.
Exactly.
equal.
Yeah. And so this allows us to get an enhancement of an SNR because now we can average over all of our lattice sites in our system.
What is the full P2? Because I would expect that the, it's like SLJ. So your L is 1, J is 3 half. What is 4 here? Meaning, what's your excited state that you're using there?
Sure. So this is the 4p3 half state of potassium 40. So the atoms start off in a 4s 1/2 manifold.
But spin is 3 half. Is that 4 referring to N?
Sorry, this is referring to N, the principal quantum number. Yeah. Yeah. Sorry. S. So our atoms. So we're thinking about this in terms of, we're kind of mixing between 2 particle and single particle basis states. But yeah, because we're working with, alkali atoms, S is a 1/2.
But the 3 half is a J.
3/2 is J. Yeah. So N here is the principal quantum number, P is L, and then 3/2 is the J of a single atom transition. Does that answer your question?
Yes, yes.
Great. Okay. So this is sort of our measurement protocol. So again, just to recap, we'll start off with the spin sigma state. We then transfer, and then this 2-photon R spectroscopy. But of course, our system, in fact, is this cubic lattice, which has some momentum zones that looks like this. And so our measurement protocol is actually through a technique known as band mapping, where we can actually map on our momentum states into quasi-momentum, which allows us to sort of take momentum space images like this, which allows us to resolve both the spin and momentum degrees of freedom. And so these are sort of data that we take in the lab for these absorption images, which allows us to say count the number of downs and ups and then measure out this magnetization. So moving on, let's actually talk about what our data looks like. This is an example spectroscopy spectrum, where on the x-axis I'm plotting the frequency of the RF that we're applying, modulo this Zeeman splitting between the up and down spins, and on the y-axis I'm plotting here this bulk magnetization as defined previously. And so what you can see here is a characteristic triplet of spectroscopy spectrum, one that occurs exactly at the Zeeman splitting. And that's simple. That just corresponds to us flipping the spin of singly isolated lattice sites that have only one atom. But in fact, it's these 2 other peaks which corresponds to us flipping from a down-down to an up-up, where the splitting is caused by this interaction energy UP. So the way that we can understand spectrum such as this is by taking the analytic solutions to that pseudopotential that I was mentioning before, which I plot for you here diagrammatically here on the right side. Here the x-axis is the magnetic field and the y-axis is the energy of the state. And so you can imagine that when there's no coupling, the spectrum of the system is just given by the harmonic oscillators. And because I'm considering the subspace of some odd parity states, I'll only consider relative motions of say 1 and 3. Which respect the symmetry of the interaction. And so that's what these dashed lines are. And what happens is, if you recall, the Feshbach mechanism mixes in some bound molecular state. And so that is going to come in with some differential magnetic moment. and it's going to exhibit this characteristic level of repulsion between my scattering states and create a spectrum that looks such as this. And so this should remind you in a sort of a discrete sort of perspective, this perspective I was talking to you earlier about this bound molecular state interacting with the scattering continuum. And so if I were to say zoom in about the transitions away from this non-interacting relative motional state, in fact, these two spectroscopic peaks corresponds to transitions to this repulsive and attractive branch like so. And so this is our spectroscopy data and how we interpret it. And so we can take this data over many, many experimental runs. Here, the x-axis is magnetic field, and the y-axis is the measured interaction energy, where this data point actually corresponds to these two over here. And what I'm plotting for you in the solid lines here are the theoretical expectations from the pseudopotential and the known properties of this Feshbach resonance, where you can see that there are both attractive and repulsive branches. You'll also notice that there's sort of this lightly shaded line, which simply corresponds to the fact that there's going to be different properties depending upon which momentum mode I'm colliding in.
So just to be clear,
Yeah.
the picture up top, I shouldn't take too seriously the fact spins are still drawn on that n=1 line. This the whole point is.
Yes,
relative.
that's going to be shift a little bit. Yeah, this is just meant to be a cartoon. Great, so we can repeat this over many, many trap frequencies. Here's at, some large one at 160 kilohertz and some slightly lower one about 90 kilohertz, still in the very deep regime. And we can see a couple of features. One is the fact that we get very nice agreement between our data and the experiment. But furthermore, you can see the fact that there's a shift in the resonance location, which is expected because of the fact that I have a 0 point energy in my lattice potential that's going to shift the resonance condition away from the free particle or the free scattering resonance location. Okay, so this is very nice, and this is already a very nice result, but it's a little bit complicated and non-universal. Is there a way that we can understand this sort of scattering energies here that isn't so specific to this particular atom and that can be generalized to other systems? And it turns out there's a way that you can do that, which is simply just by expressing the energies in terms of this, the normalized harmonic energy and the scattering volume. And when we do so, we see a very beautiful collapse of all of our spectroscopic data onto a single universal curve, which is only parameterized here by the x-axis by the inverse scattering volume, where we've normalized the energy in terms of the relevant energy scale of the system, which is this harmonic energy. And just as a reminder, you can see here that this dashed line is this non-interacting energy here, where we can see that these two branches approach away. I'd also like to point out in particular that we can see here that where our data is able to access the so-called unitary regime, which is where the scattering volume diverges, or in which case the inverse scattering volume approaches 0. So we're really in the strongly interacting limit and far away from any perturbative treatment about these interactions. We can also go one step further and also actually calculate what the wave functions for the system are. So here, over here in this non-interacting regime, we can compare, say, the pseudopotential wave function, which is in blue, to a non-interacting wave function, which is in this dash here. And also a full molecular calculation, which we call this ab initio calculations in the red dashed. And we can see this non-interacting case, the pseudopotential wave function gets the long-range behavior very well, and it looks like a non-interacting state, with the exception of the short-range character, which is totally expected because you can imagine that the pseudopotential is looking at some sort of, it's met for some boundary condition, and it's just looking at some total scattering phase. And so it's going to kind of ignore everything about the short-range probabilities. We can also do so on the non-interacting side over here. We see the same story. I'll get to your question in one moment. And we can also do this in the unitary regime, where again, we can see that the pseudopotential diverges, and also at long ranges looks very different than, say, a non-interacting relative motional mode, where in contrast, the ab initio calculations do capture some short-range behavior. I believe there was a question.
Yeah, just to clarify.
Yeah.
Scattering volume, are they something you measure empirically, or you calculate them based on your magnetic field that you're applying?
So there have been previous measurements, in fact, by Joseph's group and other groups characterizing this Feshbach resonance, where that you can actually calculate through what's called coupled channels calculation, the scattering volume as a function of magnetic field. But for the purposes of this experiment, we simply use it as a calibration and we assume some known scattering properties.
Courtney, you've taken a lot of questions, but now we remind you that.
Yeah, so we're gonna, I might go a little bit longer in anticipation of all these questions. I'll try to race through the rest of this talk. So I'll very quickly go over this. We can also say draw Rabi oscillations between this triplet down state to the triplet up state, which can actually perhaps address your earlier question earlier, Ephraim, which is the fact that I can actually drive two spin flip criterion under some sort of single spin flip tuning here, where omega-1 is the single spin flip Rabi frequency. FRF is my RFI ply, and there's some detuning between the single transition from this interaction energy. And when we do so, we see this characteristic two-tone oscillation in the magnetization as a function of hold time for this applied drive, where these fast oscillations simply correspond to off-resonant coupling of single spins, where this longer oscillation corresponds to this desirable spin flips between these down-down and the up-up states. Where this oscillation frequency is simply given by some simple three-level analysis. And so we can actually use this to and actually predict what we think this two-tone oscillation frequency should be, as well as any matrix overlap between the spatial coordinate of the system. And when we do so, we see very nice agreement between theory and experiment as a function of the inverse scattering volume for both the pair oscillation frequency and this wave function overlap between my interacting and non-interacting states. And very quickly, you'll just see that this amplitude decreases as I approach smaller inverse scattering volumes or divergent scattering volumes. And that's because the wave function has been seriously deformed. So finally, I'd like to talk about the lifetime very quickly, which is sort of the main sort of punchline of this talk, which is, okay, so we've made these interactions between P-wave pairs on these lattice sites, but can you do anything useful with them? Do they stick around long enough that you can use them in experiments? And furthermore, have I actually solved the problem of three-body loss? And so to do that, we'll conduct we're going to want to do a lifetime measurement. And so the way that we can expect the lifetime is thinking about the fact that this interacting wave function is going to have some hybridizing, it's going to be hybridized, or sorry, this interacting wave function, because of this Feshbach resonance, which hybridizes my bare states with this molecular state, will have some dimer fraction chi and some non-interacting fraction, say root chi minus 1. Where this molecular lifetime has been calculated previously to be these particular values. And so we can estimate the lifetime of our system by simply accounting by using this fraction chi here. And the way that we can estimate this is noting for a fact that when we looked at our interacting wave functions, they had very characteristic length scales. They had some sort of long range behavior, which is primarily due to the sort of confinement of each lattice site, and some short range behavior, which is a consequence of the fact that I have this bound molecular state being mixed in. So this gives us a very natural way to estimate chi by simply applying a cutoff where we notice that there's going to be different characteristic behavior at short range and long range, which I can go into more detail, but it gives us a way of measuring and estimating chi's. And so if we perform our lifetime measurement, which is simply to flip the spin to up, up, and then back down to down, down, if there's some variable wait time, we can see that the magnetization has this characteristic 1/e times on orders of tens of milliseconds at varieties of magnetic fields here, which we can also plot in terms of, we can then compare this to this estimation, which I was mentioning earlier using this short range fraction chi. And if we do so, again, we see very nice agreement between our data, which are these circles, and the theoretical expectations based upon the calculated wave functions, which are the solid lines. And also, I'd just like to point out that these squares and the diamonds here correspond to this data here. And so this is great. These lifetimes are very long in comparison to what was measured previously. So in contrast, where this lifetime was only 1 millisecond, we're now being able to measure lifetimes of over 50 milliseconds, which is 50 times larger than observed from molecules in free space. And most importantly, this model only takes into account any two-body loss mechanism, which again is specific to this atom. So it's not an insurmountable problem, which means that we've completely eliminated or not completely, but it is consistent with eliminating three-body loss, and we're only two-body limited, which means that we've sort of gotten around one of the major issues working with these P-wave systems. And so with that, I'd like to conclude what I've shown you is that by using these deep optical lattice systems, that we're able to realize elastic and unitary on-site P-wave interactions in these neutral atom systems. And furthermore, that you can use a pseudopotential to explain these interactions, which generalizes these sorts of interactions to all cold atom systems that could have these P-wave interactions. And also, we've also verified that these agree with ab initio calculations for molecular potential specific to our atom. We've also shown that these measurements can be sensitive to very fine details about these systems, such as this wave function overlap. And most importantly, in my opinion, that this lifetime is only limited by the intrinsic diamond lifetime and not three-body loss. So what's sort of next for these sorts of experiments? Well, first of all, I'm working in the very deep lattice, and if I want to look at any sort of many-body behavior, I'm going to need to turn on tunneling. And so first of all, you can just say, what happens as we turn on tunneling back on? And more importantly, can we continue to suppress three-body loss even when tunneling is enabled, which is a kind of tricky problem to still solve, but we have a couple of tricks up our sleeves, which we'll hope to try. And I think also very excitedly, sort of what will happen to, say, other atomic species which are not anticipated to have this undesirable two-body loss, in which case the only problem is going to be three-body. And so I would say the jury's still out on whether or not we can use these P-wave interactions in these lattice systems, but I would say the future is bright and there's much more work to be conducted. So with that, I'd like to thank you for your attention and open it up to questions.